Hello, this is Dr. Zach. So for today's lesson preview, you're going to show me that you remember integration. So give questions A and B a good try, and then we'll discuss your problems. Your first question was pretty straightforward. Let u equal sine of x, du follows along. You will now integrate by adding 1, dividing by your new exponent, plus c. Don't forget to replace your u value. Question B may have posed a little bit more of a challenge, but hopefully not much. If you were to let u equal your cosine x, that wasn't very useful because your du is going to be negative sine of x, and we have no sine values in our problem, so this is probably not the path to take. You will have to start using your trig identities. Cosine squared has a lovely trig identity. Keep your cosine x, replace cosine squared with 1 minus your sine squared x, and then you have dx. If we now let u equal the sine of x and du is equal to your cosine of x dx, you will be able to integrate this problem. We will have 1 minus our u squared, then your du gets substituted in. Now, be wary. When you find this antiderivative, you're going to have u minus your u squared over 2. Don't forget that plus c. The problem is not done. Fill your sign back into this problem, and you will have completed it. Notice your previous question B had an odd exponent, and you were able to take your odd exponent so that it splits into 2 parts, and then you were able to use u substitution. Let's see if we can do something similar with example 1. We have the sine to the 5th power of x. If we had a nice little sine of x all by itself, with the dx, wouldn't it be lovely if we could let u equal the cosine of x so that our du would become the sine of x dx? And don't forget your negative. So let's see if we can arrange for this to happen. Sine to the 5th power of x is sine of x times sine to the 4th power of x, but we still have this nice little cosine squared x in the problem. All right, if we let u equal the cosine of x, that's going to help us out with the cosine squared, but we're still going to have a challenge with the sine to the 4th power. However, we are clever people. Let's keep the sine of x, which came from that odd exponent, rewrite the sine of x using, again, a trig identity, 1 minus our cosine squared x, but this is raised to the 2nd power. Now we haven't messed with the cosine squared x, and now we have dx. So now let's take a closer look. We have cosine, which can be replaced with u, another cosine that can be replaced with u, and then our du could be negative sine dx. So let's rewrite this problem. We have the negative integral 1 minus u squared, quantity squared, u du. All right, it's a little bit messy, but we can multiply this out. We will have 1 minus our 2u squared plus u to the 4th, and that will be multiplied by u du. More algebra, because algebra is so useful. We're going to have u minus 2u to the 3rd plus u to the 5th. And now we are ready to integrate. And once you integrate, don't forget your plus c and to replace that u value. It's not finished. You need to finish it. All right. Okay, that was a nice little trick we did before, but I'm looking at example 2. If I let u equal the sine of x, my du, of course, is the cosine of x. So that's not useful. We need a different plan. Okay, so what if I were to split it up? What if I have a sine of x and sine cubed of x? Still not very useful because I don't have a cosine involved. Well, what if I did sine squared x, sine squared x? I don't know that that's useful either. What if I had sine squared x and I replace this with 1 minus cosine squared x? Again, Not useful because I need cosine x. Well, what if I let u equal cosine x? Maybe that'll be useful. So du is negative sine x dx. Unfortunately, I will have too many sine functions. So at this point, you should be asking yourself, is there another trig identity that I should use? And yes, there is another trig identity. The sine squared x should be equal to 1 minus the cosine, and it's not cosine x, it's going to be the cosine of 2x. This is your half angle identity divided by 2. Okay, now why is this better? We just took a function that had a squared and changed it into one without a square. And that is reducing our problem to make it easier to deal with. So let's try that. Going back, we have the integral sine squared x times sine squared x dx. I'm going to use my reduction formula. So we have 1 minus the cosine of 2x over 2 times 1 minus the cosine of 2x over 2 dx. Let's do a little bit of algebra. Factor out my 1/4. Multiply. I have 1 minus 2 times the cosine of 2x plus the cosine squared 2x dx. Now, as I look at the problem, I know how to integrate the first term, the second term, but I don't know the third term. Ran into the same problem. It looks better than what I started with, but I need another rule. Yes, another reduction formula. So what do we know about the cosine squared x? Well, your cosine squared x is equal to 1 plus the cosine of 2x over 2. So again, that's going to take something squared and reduce it so that we will be able to integrate. All right, now let's see how we can rewrite this formula. We now have our 1/4, the integral. Here's my 1 minus 2 cosine 2x. Use the reduction formula for cosine, and we will get plus 1 plus the cosine. We have to take that angle, 2x, and double it, which makes it 4x, and we still divide by 2. Don't forget dx. All right, now we're ready to integrate. We didn't integrate the last one. Let's see what this one looks like. 1/4 x minus 2. The antiderivative of the cosine is your sine. Here's your 2x divided by 2 plus 1/2 x plus your sine 4x divided by 8. And please, after all of this work, don't forget your plus c. So far, what we should recognize is if we have odd exponents with our trig functions, that's really helpful. If we have even exponents, then perhaps we can use a trig identity and rewrite it using your 1 minus sine squared x or 1 minus cosine squared x. But if you aren't able to use u substitution on your problem, then you're going to have to use your reduction formula. Let's look at example 3. Now we're playing with tangent and secant functions. So let's think. If I were to let u equal the tangent of x, I would need to have du is equal to the secant squared x. Now, I don't know if you noticed this, but we have a square root for the secant. That might not be useful. All right, let's try it again. What if we were to let u equal our secant x, then du would need to be equal to the secant x tangent x. All right, so this looks tricky. Let's do some clever algebra. We know that our tangent cubed can be rewritten as tangent squared x times a tangent x. There we go. And we have our square root of secant in my denominator. It would be so lovely if I had that extra secant in the numerator. Well, you know what? You are clever. Let's put it in there. Secant x is now in the numerator. Haha. But we now need to divide by the secant x. Don't forget your dx. So when we relook at the problem, we have a tangent squared left in the problem. I would love to only have secants in this problem. And if you'll recall, we do have an identity for the secants and tangents. We know that the tangent squared x is equal to the secant squared x minus 1. Substitute. So this gives us a secant squared x minus 1, which is replacing your tangent squared, divided by, let's combine secant and square root of secant. That gives us secant to the 3/2 power x. And wait, we still have the tangent x, secant x in the numerator, which is a good thing, because now if I let u equal the secant x, my du is exactly what I want it to be, tangent x, secant x, dx. And then we will substitute. We have u squared minus 1. All of this is my du divided by u to the 3/2 power. Clean this up. This is going to be equal to u to the negative 1/2 power minus u to the negative 3/2 power du, and we can now integrate this problem. Go ahead, finish your problem. Don't forget to substitute your u, which is secant x, back into the expression. Example 4. For this problem, we're determining an average value of a function. It's been a while since we did an average value. So if we are looking for the average value of a function, f of x average is going to be equal to 1 over b minus a, the integral from a to b of our function f of x dx. So that is the formula for the average value. So we want 1 over pi divided by 2 minus 0, the integral of our cosine to the 5th power x dx, and we're going to integrate from 0 to pi over 2. So there are actually two ways to do this problem. The first way, we would rewrite the cosine to the 5th power as our cosine x times the cosine to the 4th power x dx. Then we can substitute in for our cosines. We've got 2 over pi, integral from 0 to pi, cosine x, multiplied by our 1 minus sine squared x, and that's going to be squared because it's to the 4th power dx. Yes, and then we will let u equal the sine of x. Your du is going to be equal to our cosine x dx. Replace everything. We have our 0 over pi times the integral from 0 to pi. The cosine x and dx are going to be replaced with my du, and then I'm going to be left with 1 minus u squared. Multiply that out. It's 1 minus 2u plus u squared u to the 4th power du. All right, we're going to finish up some work on this one. Integrate. We still have our 2 over pi. Then when we find our antiderivative, it's 1 minus 2 u to the 3rd over 3 plus our u to the 5th over 5. And we're going to evaluate this. Remember, these are u values, and the 0 to pi that I have in here are x values. We want to keep that in mind. But when x is 0, we get the sine of 0 for the u value, which is 0. And then we want the sine of pi. Wait a minute, this should be pi over 2. You probably knew that all along. So when we put our pi over 2 in, here's my pi, there we go, that's better. We get 1. Substitute, we have 2 over pi times, and when you simplify, you're going to get 8 over 15. So second way to do this problem is using a formula called Wallace's formula. And this formula is actually really cool, quite clever. For whatever reason, AP always has a problem that could be solved using Wallace's formula. So the idea behind Wallace's formula is if you have a cosine to a particular power it has to be exactly going from 0 to pi over 2, then there is a nice little algorithm we could use to solve it. So here's Wallace's formula. If your n value is odd and greater than or equal to 3, and you're integrating from 0 to pi over 2, your cosine to the nth power can be written quite simply as 2/3 times 4/5 times 6/7, all the way until you get to the last exponent in our problem. Now, if you have an even exponent, cosine to the nth power of x, you just follow a little bit different formula. You've got your 1/2 times 3/4 times 5/6 until you get to the n, but you also need to use the multiplier pi over 2. So when we had our problem on the last page, it was 2 pi, the integral from 0 to pi over 2, times the cosine to the 5th power x dx. You can see that n is odd in this problem, so we will have 2 over pi multiplied by 2 over 3 times 4 over 5, and that is the end of the problem. But as you can see, it's a very specialized problem, and you can solve your problems differently if you choose to. All right, so we have guidelines for evaluating your integrals involving powers of sines and cosines. Don't forget that if both the sine and cosine are even and non-negative, you must use a reduction formula. Go ahead, let's practice these 4 questions and see what you can do with them. For question 4, did you notice that you had to use your reduction formula for your sine squared x? But not only that, after that, you needed to use integration by parts. I hope it was a good reminder for you. Example 5 is done very similarly to what we were working on earlier. As you take a look at it, think about what u should equal. U is going to be equal to, let's try a secant of 3x, in which case your du should be equal to a secant 3x tangent 3x multiplied by 3 with a dx. So we could do that if we take one of these secants, keep the other 3 together, leave 2 of the tangents together, then we will have a secant 3x tangent 3x that we will be able to use for our du. So that's allowing u to be secant x, but then we're left with this tangent. Oh, what a bummer. Fortunately for you, you know an identity for tangent squared. So we're going to rewrite our problem. Secant cubed 3x multiplied by our secant squared x minus 1. And then we still have our secant 3x tangent 3x dx. Next, we're going to do our u substitution. We will have u to the 5th power minus u to the 3rd power with du. Afterwards, you can integrate with no problem at all. So example 6 is one of my all-time favorite problems. Let's take a look at it. If I try my u substitution, u equals secant x, I don't have a secant tangent. The tangent's totally missing, so that's not going to be useful. I could try trig sub, but let me tell you right now, it's not going to help. So what we're going to do is look at this problem differently. We have the antiderivative of our secant squared 3x times the secant of 3x dx. As you look at your problem, did you notice that you know the antiderivative of the secant squared 3x, but you also know the derivative of that secant 3x. So this is integration by parts. So u is going to be equal to our secant 3x, and dv shall be equal to our secant squared 3x dx. So then du is going to be, the derivative of secant is your secant 3x tangent 3x multiplied by 3. And your v is going to be equal to the tangent of 3x divided by 3. Now, when we multiply, we get this is equal to u times v, so that is going to be a secant 3x tangent 3x divided by 3 minus our v du, so that will give us a secant, the integral of the secant 3x tangent squared 3x, then we're going to multiply by 3 1/3. Don't forget your dx. I did forget it, that's shame on me. All right, now look at our secant 3x and the tangent 3x. We could take a look at this problem and think of it this way. What if we were to replace the tangent squared 3x with its trig identity? So let's go ahead and do that. We have 3x tangent 3x divided by 3 minus our integral. Here's my secant 3x, and then the tangent squared 3x. What's that equal to? You should know your trig identities. And we're going to get the secant squared 3x minus 1 dx. All right, a little bit more algebra. We love algebra. Keep rewriting everything over. And we have minus, we'll have the integral of our secant cubed 3x. Two negatives together make this a positive, don't forget dx, plus your integral secant 3x and dx. All right, now let's take a look at this. Okay, so we know the part, you know the answer for this part. You might know that one from last year's work. This is plus 1/3 the natural log absolute value secant 3x plus tangent 3x. Here we go, there's that part. But this one, did you notice it's what we started with? So we're going to add that to both sides, and we now have 2 integral secant cubed 3x dx is going to be equal to our secant 3x tangent 3x divided by 3 plus this 1/3 natural log absolute value secant 3x plus tangent x, then tangent 3x, then we will divide by 2, and when we divide by 2, let's see what happens. Divide by 2, the only thing left is to throw on our plus c. So that's not written very neatly. Let me try again, and you can see that this problem was integration by parts, but it also went into circles, and you had to remember a rule from your AB course for the antiderivative of a secant. Isn't that so much fun? So the next set of rules are not actually on your AP exam, but you should know they exist. Take a look at example 7. The sine has the angle 5x and the cosine has the angle 4x. All the other problems that you've been playing with for the last 2 years, the angles have been the same. But that is not necessarily true. Fortunately for us, we have other identities that we can use to rewrite our problems. And these are your angle addition formulas and angle subtraction formulas. In this case, we're going to take m minus n, so that will be 5 minus 4 is 1x. Rewrite that, plus, and then we'll have the sign of m plus n, which makes it 9x. Here is my dx, and now the problem is super easy to integrate, because without this, we would not have known how to integrate our problem. So we have 1/9 with a negative. Here's my cosine 9x, and of course, do not forget your plus c. So today's lesson, one more time, was on integration using trig identities. Know your trig identities.